In the second part of the lecture on examples of decision trees, we should talk about the gradient boosted regression tree or gradient boosting machines. Gradient boosting regression tree is another ensemble method that combines multiple decision trees to create a powerful model. Despite the regression in the name, these models can be used for regression and classification both purposes. In contrast to random forest approach, gradient boosting works by building the trees in a serial manner, where each tree tries to correct the mistakes of the previous trees. By default, there is no randomization. In a gradient boosted regression trees, strong pruning is used. Uh, and no randomization is there in the gradient boosting regression trees, but the strong pruning is used in the gradient boosting regression trees. Gradient boosted trees often very shallow of the depth and maybe up to the depth of 5, which makes the model to use the less memory and make the fast predictions. The main idea behind gradient boosting is to combine the many simple models. We combine the weak classifiers like the shallow trees. Each tree can provide a good prediction on part of the data, and more trees are added iteratively to improve the performance. So here is the example of the decision trees illustrated by a figure. So here is the boosting ADA boost method, where the data is separated into the training and the testing set, and then bags of the data they are created. Bag 1, bag 2, and bag 3. Bag 1 of the data is created from by randomly sampling from the training data. Then the model is trained on this data B1, and then for testing of the model 1, we use all the training data, and then if they we check that for which points this model makes poor predictions, and the poor predictions they are represented in this figure as pink points. So then we make a second bag of the samples, and second bag of sample is chosen such that it takes the data from the training data and also those sample points for which the prediction was wrong, and we type it is made a little high the probability of such points for which the prediction was wrong, shown by pink points. So here are the pink points. So the green points are original training data, and pink points are the training data for which the prediction was wrong by the model 1. So then we make a model 2, and for model 2, this data is fed, and this stage it is used both the model 1 and model 2, and then predictions are made, and then wrong predictions are also noted down, and these wrong predictions along with the training data that is fed to the third bag of the data. So it's keep on doing this. So in this way, this model is a serial that the model 2 tries to correct the mistakes of model 1, and model 3 tries to correct the mistakes of model 1 and model 2. So here we talk about this. We built the first bag of data from the random sample training data set and train the model on this data set. Next, we test the trained model on all training data. Here we test the model 1 on all training data and note which samples or objects would our model would make the mistakes. We built a new data set by again, next we built a new data set again by randomly selecting samples from the training sample, but this time each of them has a certain weight depending upon the error of the trained model. So these pink points, samples that deliver the largest error are more likely to get into the new data set. And this new data set has probability of samples which make a high error. With this data, we train the model. Now we test our mini examples of the two currently available models. Now we have the model M1 and model M2, and we test this bag 2 on these model M1 and M2, and re-memorize the difficult samples and try to figure out the difficult samples on which they were mistaken. Further, in the same way, we build new data set and new models. We are keep building new data set and new models that correct the errors of existing samples, existing ensemble, that make a correction for the existing ensembles. So, of course, in this way, difficult patterns can change as our system grows. The difficult patterns they can change. In bagging, we build several data sets by randomly selecting them from the training set. So this is bagging, where we make the different bags of the data from the training set. The idea of boosting is very similar, only the data is chosen more smartly on which the existing models are wrong and which still need to be learned better. And bagging and boosting. What is the boosting? We are choosing in the second bag, we are choosing the data for which there was error. In the third bag, we was choosing the model where we try to improve the we try to increase the probability of samples for which the error was higher, like these samples shown as a pink box. So this is called bagging. This is called bagging, and increasing the sample, increasing the error sample is called boosting. Gradient-boosted trees are frequently winning entries in the machine learning, and they have been widely used for industrial applications. They are generally a bit more sensitive to parameter setting than random forest, but they are little more sensitive to parameter setting, but can provide better accuracy if parameters are set correctly. If we can set the parameters correctly, so it is a good option. Apart from the pruning and the number of trees in the ensemble, another important parameter of gradient boosting is the learning rate, which controls how strongly each tree tries to correct the mistakes of previous tree. How how strongly, how better the tree tries to correct the mistakes of previous tree. A higher learning rate means each tree can make a stronger corrections. Higher learning rate, a strong correction, allowing the complex model and adding more trees to the ensemble, which can be accomplished by increasing the n estimator. We will need and more. We have to increase the n estimators for getting more trees. Also increases the model complexity, but it also higher learning rate. It increases the model complexity. It increases uh, the more trees and model complexity, as the model has more chances to correct mistakes on the training set. So here is an example of using gradient boosting classifier on breast cancer dataset. By default, we have 100 trees and a maximum depth of 3 on a learning rate of 0.1. So here we run it. See, okay, sorry for a minute because I have not done all that. Because just a minute. Today I have not run this code about this part, and so therefore it was making an error. So I do it again. So here we get the training set accuracy of 100% and test set accuracy of 95%. So this may lead to say that there is overfitting because training set has 100% accuracy, and there is some significant difference between training and test. So now what we do is that we apply the strong pruning and keep the maximum depth to 1. So now in the previous, in this case there was no maximum depth, uh, but now we are making the depth equal to maximum depth is equal to 1. So and now we see that the accuracy is training accuracy is 99% and test accuracy has increased to 72%. So this method decreases the model. Okay. So as we can see that as for this method of decreasing the model complexity reduce the training set accuracy as expected. In this case, lowering the depth of the trees provided a significant improvement of the model. We decrease the depth of the decision tree, but it increased the significantly increased the performance, the test set accuracy of the model. So as for other training, other decision trees based models, we can again visualize the feature importance. Now we can get to the feature importance and see that what the feature importance is when we have the 100 trees and the maximum depth is 1. So I run this part of the code and see, and we notice that a lot of the features have been suppressed to 0. We can see that the feature importance of gradient boosting trees are somewhat similar to the features of the random forest. Though the gradient boosting completely ignored some of the features. Gradient boosting, it completed some of the features, but some of the other features, they are the same like we use in the random forest. As both gradient boosting and random forest perform well on similar kind of data, the common approach is to first try random forest, which work quite robustly. In random forest work well, but prediction time is premium is high, or it's important to squeeze out the last percentage of accuracy from the machine learning model moving to the gradient boosting for often happens. So first we try the random forest and check if it's working very well. And if there is no memory constraints, then it's okay. Memory or time constraint, then it's okay. Otherwise, we try the gradient boosting algorithm. If you want to apply gradient boosting to large problem, it might be, if you want to apply the gradient boosting to a large scale problem, it might be worth looking into the XGBoost package that is in the Python interface, which at the time of writing is faster. So it is the faster. So this was about the gradient boosting algorithm. So now we sum up this topic and talk about its strengths, weaknesses, and parameters. Gradient boosting is among the most powerful and widely used method for supervised learning. And their main drawback is the carefully tuning of the parameters. How we can carefully tune the parameters and may take a long time to train. Similar to other tree-based methods, the algorithm works well without scaling on a mixture of binary and continuous features. As with other tree-based models, it also often does not work well on high-dimensional data, high-dimensional sparse data. On high-dimensional sparse data, it often does not work well. The main parameters of gradient boosting trees models are the number of trees, n estimators, and the learning rate, which control the degree to which the tree is allowed to correct the mistakes of previous trees. These two parameters are highly interconnected. For example, lower learning rate means that more trees are needed, so it is a vice versa. So we have to be carefully choose that. Lower the learning rate, the more trees are needed to build a model for similar complexity. In contrast to random forest, where higher n estimator value is always better, increasing n estimator in gradient boosting leads to a more complex models, and which may lead to overfitting. A common practice is to fit n estimator depending upon time and memory budget. So time and memory budget are very important things. We have to select the n estimators based on that, and then search the different learning rates. Another important parameter is max depth or leaf node, maximum leaf nodes. How many nodes we need in this forest for each tree. Usually max depth is set to very low for gradient boosting, and it may be up to 5 splits is enough for the gradient boosting algorithm. So this was all about the lecture of the examples of the decision tree, where first we talked about random forest, and in the second part of the lecture we talked about gradient boosted algorithms. So okay, thank you.